In standard building construction, you price the materials, you pay for the labor, and, well, you build the house.
Right, it's pretty straightforward.
Yeah, exactly. But in civil engineering, the most expensive line item on a billion-dollar invoice might be for something that literally no one can see yet.
Oh, absolutely. It's wild.
So how do you put a price tag on the completely unknown? I mean, when you're looking at massive infrastructure projects like highways literally cutting through the center of mountains, sprawling railways stretching across the horizon, or massive dams holding back millions of gallons of water, you are pricing out a battle against nature, geology, and time.
You're pressing the earth itself, basically.
Exactly. So today's deep dive is all about decoding the DNA of how those costs are structured. We are looking at a stack of lecture notes and guidelines detailing my CESMM2.
Which is quite the acronym.
It really is. For those of you deep in the industry, you already know that stands for the Malaysian Civil Engineering Standard Method of Measurement. And it essentially functions as the master playbook for how professionals mathematically structure the unpredictable.
Yeah, I mean, it functions as a survival guide, frankly.
A survival guide.
Completely. Without a rigorous standard like this, these mega projects they'd collapse under their own financial weight before a single shovel ever hit the dirt. We are looking at a methodology designed to enforce cost transparency across an industry where the ground underneath your feet is, well, literally shifting.
Wow. Okay, so the roadmap for this deep dive is packed. We are going to explore why civil engineering projects are inherently riskier than standard building projects, how industry professionals tame that chaos using a bill of quantities, the secret coding language they use to categorize the work, and the massive hidden costs of heavy machinery. Okay, let's unpack this.
Yeah, to really grasp the mechanical necessity of a system like MyCESMM2, we first have to dissect why civil engineering is fundamentally a different beast compared to regular building construction.
Right. It's not just a bigger building.
No, not at all. The rules that govern a commercial office building simply break down when you apply them to, say, carving out a new reservoir or laying down expansive sewerage works and water reticulation systems.
The core difference seems to be the ratio of planning to reality, right? Like when you're building a commercial high-rise, you have a relatively controlled environment.
Very controlled. You own the airspace, mostly.
Yeah. You have a surveyed plot, you pour a foundation according to hyper-detailed architectural plans, and you build vertically into empty space. You generally know the physical boundaries of your workspace.
In standard building works, you can map out almost every material detail before you even begin. But civil engineering works, especially marine works, major earthworks, or tunneling, they operate with a massive degree of built-in uncertainty.
Which is terrifying when millions of dollars are involved.
Oh, it's a nightmare for estimators. The source material highlights a critical vulnerability here. At the pre-tender stage, meaning the period before the contract is even awarded and physical work begins, the actual work involved simply cannot be ascertained properly or correctly.
Wait, really? So you're bidding hundreds of millions of dollars on a project where the full scope is, like, scientifically impossible to know in advance?
Exactly. If we connect this to the bigger picture, these projects happen in adverse, highly unpredictable conditions. You're often dealing with underground environments, unpredictable water tables, or underwater structures.
Right, the stuff you can't just take a drone photo of and understand.
Exactly. And because of this environmental chaos, civil engineering projects are usually tendered with much less detailed design than standard building works. I mean, you cannot perfectly plan for what is 50 feet underground until you actually start excavating.
It sounds like building a house is like following a Lego instruction manual, whereas civil engineering is like being told to build a Lego bridge, but half the pieces are buried in a mud pit and you don't know what shape they are yet.
Yes, that's exactly it. And you don't know if the foundation for your Lego bridge is going to hit solid bedrock or a subterranean swamp 10 feet down.
Oh, man, a subterranean swamp.
Yeah. You know you need to cross the river, and you know the load-bearing requirements, but the geological reality is a massive, massive variable.
So if the contractor is dealing with that level of uncertainty, they can't just, submit an invoice that says, build bridge $100 million.
No, the clients would laugh them out of the room.
Right. So the notes say that a civil engineering bill of quantities, the BQ, functions very differently from a standard building BQ. The guidelines explicitly state that a civil engineering build item merely identifies the work.
Yes, that's a crucial distinction.
It is not intended to fully describe the nature and extent of the work, but I gotta say, that phrasing, merely identifies, It feels like it leaves a massive legal loophole for errors.
It shifts the burden of interpretation, for sure, because the BQ item merely identifies the task. Estimators cannot simply look at a line item on a spreadsheet and instantly know the cost.
They can't just look up dirt removal and write down a price.
Exactly. They are forced to act almost like forensic accountants. They have to extract the real scope, the context, and the physical limitations from the engineering drawings, the detailed specifications, and the specific conditions of the contract. The BQ is just the index. It isn't the whole encyclopedia.
Which brings us to the actual preparation of the bill of quantities as defined by the MyCE SMM2 guidelines. If these projects are so wildly unpredictable, and the BQ merely identifies the work, the industry desperately needs an ironclad standardized structure for that identification.
They need a shared language.
Yeah, we need a way to mathematically tame the beast so everyone is bidding on the same reality.
And that's where Section 4 of the guidelines comes in. It outlines exactly how this bill of quantities must be structured to maintain that shared reality. It dictates that the BQ must comprise very specific sections.
Okay, lay it out for me.
So you have Section A, which is the preamble. This sets out the rules of engagement and specific measurement principles applied to the project. Then you have Section B, which houses the work items.
And Section B is where the actual project gets broken down into localized, digestible parts. Like the source gives examples where Part 1 might be general items, Part 2 is bridge number 1, Part 3 is bridge number 2, Part 4 is road work, and so on.
Right, it physically compartmentalizes the chaos.
Breaking it down geographically, like that must serve a larger administrative purpose, right?
Oh, it serves a critical twofold purpose across the life cycle of a project. First, in the pre-contract phase, it provides essential information on the items, descriptions, and quantities required.
So it gives everyone a level playing field.
Exactly. It gives all bidding contractors a standardized baseline to understand the scope, even with the inherent environmental uncertainties we just discussed.
So what does this all mean? If the pre-contract purpose is setting that baseline, I have to imagine the post-contract purpose is about defending yourself when things inevitably go wrong. Like when that Lego bridge hits the subterranean swamp and the design has to pivot.
You nailed it. The post-contract phase is exactly where the rigid structure of Section B staves the project from descending into endless litigation. Once the work is underway, the price BQ becomes the definitive baseline for valuing the work that has actually been executed.
Ah, so it's the ultimate scorecard.
More importantly, it serves as the mathematical basis for valuing variations. When you hit that swamp and need to drive piles twice as deep, the BQ provides the pre-agreed rates.
You don't have to negotiate the price of a cubic meter of concrete from scratch.
Exactly. You just apply the BQ rate to the new required volume.
Man, without that standardized baseline, every time they hit a rock underground, the entire project would grind to a halt while lawyers argued over the cost of an excavator.
It would be absolute paralysis.
But looking at the evolution of this, the sources mention an older standard called SMM2. SMM2 is primarily used for building works, but got stretched to cover civil engineering. And then MyCE SMM2 was brought in to replace it.
Yeah, MyCE SMM2 is a rigorous adaptation of international standards,
Yeah.
specifically CESMM3 and CESMM4 from the UK, but it's blended with local practices. SMM2 was fundamentally inadequate for civil engineering.
Why was it so bad?
Well, because it was designed around standard building trades like bricklaying or carpentry. Civil engineering revolves around heavy, continuous operations like mass earth moving or large-scale concrete pouring. You can't measure a mountain like you measure a brick wall.
Right, that makes total sense.
So the goal of MyCE SMM2 was to establish a single standard methodology of measurement that actually reflected civil engineering realities across the local construction industry.
It creates absolute cost transparency. When every contractor uses the exact same operational standard to measure the work, it ensures competitive and consistent pricing during the bidding process.
It levels the playing field completely.
Yeah. It allows estimators to easily benchmark against past projects for future cost comparison. When the rules of measurement are universally understood, it strips away the ambiguity that leads to inflated estimations or post-contract disputes.
To achieve that level of universal translation, though, MyCE SMM2 relies on a highly specific classification and coding system to categorize literally every single operation, material, and labor cost.
Everything gets a code.
Every single thing. This is detailed in Section 3 of the guidelines. Coding and numbering of items. The entire scope of civil engineering work is classified into alphabetical classes from A to W.
Okay, the source notes give us a clear look at this structure. Class F is earthworks. Class I is concrete work. Class O is pipework. So if an estimator is looking at a massive ledger, they instantly know that anything starting with an F involves moving dirt around.
Instantly. It's a visual shortcut.
But it gets much more granular than just a letter, doesn't it?
Oh, way more granular. The alphabetical class is just the top of the hierarchy. The system uses a numbered coding structure to define the specifics of the work, and there are strict mathematical rules governing this numbering. For instance, within any work classification, the highest number listed is always an 8.
Wait, if the standardized numbers only go up to 8, that leaves a glaring gap. What happens when a completely new technology or a unique descriptive feature is required on a modern project?
The system intentionally reserves the digit 9.
Oh, that's smart.
Yeah, whenever a completely new descriptive feature is needed that doesn't fit the standard classifications, the estimator assigns it a 9 in the appropriate division. It's a built-in future-proofing mechanism.
So 9 is like the other category, but for innovation.
Precisely. Furthermore, if you need to identify additional descriptive features beyond the standard categories, you add an extra digit after the basic code number to expand the hierarchy.
The notes also detail the use of asterisks, which act as summaries. The example given is I-13.
That asterisk is a crucial shorthand. If you see I-13 on a document, it means the item is referring to all the sub-items in that grouping, from I-131 all the way up to I-138.
So it's a way to roll everything up.
Yeah. It is used specifically to summarize group coding in what estimators call the taking off list.
Okay, let's actually define the mechanics of that, because taking off and working up are mentioned heavily in the source. Taking off means, what exactly?
Imagine an estimator in a back room with a massive set of blueprints.
Okay, I'm picturing it.
Taking off literally means they are physically taking the dimensions off the engineering drawing, like the length, width, and depth of a proposed trench, for example, and writing them down on standard dimension paper.
And working up.
Working up is the subsequent mathematical process where they take those raw scale dimensions and square them into total volumes, areas, or tonnages.
Which makes total sense of the coding system. The A to W codes ensure they don't lose their minds while doing the math.
It organizes the data beautifully.
Right. It guarantees that one estimator isn't calling a task dirt removal while another calls it soil excavation. They both just code it under Class F.
Exactly. It removes the semantics.
But here's where I want to push back on the guidelines a bit. I'm looking at these notes, and it says, this coding is brilliant for maintaining consistency during those exact stages. But then, it explicitly states that the coding and numbering of items is optional in the final bill of quantities.
It does say that, yes.
Why on earth would you build this elaborate, highly structured secret language, train an entire industry to use it, and then make it optional on the final document?
I get why that seems counterintuitive. But you have to separate the process of estimation from the presentation of the final contract. While the codes might be optional in the final printed BQ presentation that goes to the client, those code numbers are heavily, almost mandatorily used during those taking off and working up stages to maintain mathematical risk.
But aren't you risking the client, or even the project managers on site, misunderstanding the final bill if you strip out the universal translator? If you take away the codes, you are back to relying on text descriptions, which we already established only merely identify the work.
It's a fair concern, but the client generally doesn't need to see the underlying database structure. The client needs to see clear, understandable descriptions of what they are paying for, grouped logically by physical location, like Bridge 1 or Bridge 2.
They just want the bottom line.
Exactly. The code is the scaffolding used to build the estimate safely. Once absolute uniformity is achieved by the estimating team and the data is securely compiled, you can take the scaffolding down for a cleaner presentation.
Ah, I see.
The mathematical rigor happened behind the scenes. The final printed bill just reflects the outcome of that rigorous process.
So if the codes are the scaffolding we take down, the client still sees the final price. And looking at these notes, the way that price is actually calculated brings us to a massive evolutionary leap in my CESMM2. Here's where it gets really interesting. It accounts for how the work is actually done, not just what is being built.
This is perhaps the most crucial shift, detailed in Section 6, method-related charges. To understand why this is revolutionary, we have to look back at that older standard, SMM2. Under SMM2, pricing was predominantly influenced by the project's physical location.
Which makes sense for building construction.
Yeah.
Erecting a steel frame high-rise in the middle of a congested downtown financial district is going to cost significantly more in logistics, traffic control, and material storage than building a warehouse in an empty industrial park outside of town.
Of course. Location dictates the difficulty for a building.
But civil engineering costs do not just scale based on location, they scale drastically based on the method of construction. The guidelines explicitly highlight that civil engineering involves bigger and complicated machineries, whereas standard building works generally use smaller and simple machineries.
The cost of a civil project is deeply tied to the massive equipment required to execute it.
Let's walk through a tangible scenario for you listening, just to see how this actually hits the spreadsheet. Imagine two different contractors bidding on the exact same project, excavating a 5-mile trench for a new water main.
Okay, good example.
Contractor A is a smaller firm. They plan to use a fleet of standard small excavators. Their mobilization costs, getting the machines to the site, are relatively low, but because the machines are small, it's going to take them 3 months of continuous operation and high labor costs to dig the trench.
Right. Low setup, high operational time. Now look at Contractor B. They're a massive firm, and they own a custom-built specialized trenching machine. The cost to disassemble, transport, and reassemble that massive machine on site, their mobilization cost, is astronomical.
It's a huge upfront hit.
However, once it's running, it can dig the entire 5-mile trench in just 2 weeks, drastically cutting their labor and operational time.
Under the old system, rolling all those completely different operational costs into a single generic excavation rate per cubic meter would skew the bidding process, right?
It would make Contractor B look artificially expensive on paper if you just looked at a flat rate. MyCSMM2 forces them to break this out using method-related charges.
Which creates a distinct separation between fixed charges and time-related charges.
Yes. Contractor B has to list their massive mobilization cost as a fixed method-related charge. Contractor A has to list their extended operational timeline under time-related charges.
The method chosen to execute the work massively swings the overall price structure, far more than just the location of the site.
Exactly. It prevents contractors from hiding massive equipment costs inside inflated material rates, giving the client a true transparent look at what they are paying for.
I was looking at the actual measurement rules associated with these operational costs, and the level of contractual pedantry is amazing. These hyper-specific rules show just how much precision matters when millions of dollars are on the line. The rules of measurement leave zero room for assumptions.
No room at all. What's fascinating here is a prime example is the rule for extra over items. This is an additional charge levied for work over and above normal operations, usually applied during excavation.
The classic example in the notes is when you are excavating what the initial surveys indicated was standard earth, and suddenly your excavators scrape against solid, unyielding rock.
The worst sound a contractor can hear. You've already measured, coded, and priced the excavation volume for earth. But removing rock requires entirely different machinery, vastly different time frames, and sometimes specialized blasting permits.
You can't just dig it out with a bucket.
No, you can't. Instead of canceling the old rate and trying to reprice the entire hole, the contractor charges an extra over rate. They get the base rate for excavating the volume, plus a premium extra over rate, specifically for the volume of rock encountered.
It is an elegant mechanism. It protects the contractor from catastrophic losses due to unforeseen geology, and it protects the client by ensuring they only pay that premium rate for the exact measured amount of rock actually removed.
It's fair to both sides, which is the whole point of the standard.
And then there is the hyphen rule. A single hyphen in this contract can dictate thousands of dollars in valuation. The source states that a hyphen between two dimensions means a range that includes everything exceeding the first number up to and including the second number.
It creates incredibly rigid, distinct pricing tiers for tasks like trench depth. If a built item specifies a depth measurement of 0.5 meter, 1 meter, the estimator isn't just eyeballing a shallow trench.
They aren't just guessing.
No. Mathematically, that hyphen dictates a depth starting exactly at 0.51 meters up to 1.0 meter inclusive.
So if your trench is perfectly leveled at 0.5 meters deep, it falls into a cheaper pricing tier. But the moment the excavator digs to 0.51 meters, just 1 single centimeter deeper, you cross the threshold of the hyphen.
And boom, you're in a new bracket.
And the entire volume of that deeper section is now priced in the more expensive 0.5 meter to 1 meter bracket. Precision isn't just about good engineering practices here. Precision is literally the currency of the contract.
It is entirely an exercise in risk allocation. Civil engineering is inherently dangerous, unpredictable, and volatile. What MyCSMM2 provides is the mathematical and contractual framework to quantify those risks fairly and transparently.
It puts a safety net under the chaos.
It ensures that when the unpredictable happens, and in underground construction it always happens, there is a pre-agreed, mathematically sound system for how to price the fallout.
We have covered a massive amount of ground today. We started in the wild, undocumented risks of digging into unknown geological realities and saw how the industry refuses to just accept that chaos.
They fight back with structure.
Exactly. They tame it by creating a rigorous structural baseline with the bill of quantities. We examined the transition from building-centric measurements to the MyCESMM2 framework.
Which is a much better fit for heavy civil work.
And we explored the A-to-W coding system that categorizes everything from massive earthworks down to pipeworks, acting as the foundational language for estimators during the taking off and working up stages.
A language that keeps everyone on the same mathematical page.
And we uncovered the crucial inclusion of method-related charges, proving that in heavy civil engineering, detailing the mobilization and operation of the massive machinery used to build the infrastructure is just as vital as pricing the materials themselves.
Ultimately, what this standard represents is an attempt to map the unmappable. It takes the vast, unpredictable forces of nature and heavy industry and confines them within a spreadsheet governed by precise rules, extra overpremiums, and, well, hyphens.
Even if you are never going to bid on a highway expansion or a hydroelectric dam yourself, understanding this framework reveals how professionals mathematically structure and quantify the unknown.
It's the hidden logic behind the modern world.
It is how they prevent billion-dollar projects from bankrupting cities and construction firms alike when the blueprints meet the reality of the mud. It is risk management on a monumental scale.
It provides a shared, objective reality for both the client and the contractor. Without that standardized language, every unforeseen boulder or weather delay would plunge the project into endless arbitration.
Which leaves me with a final thought for you to mull over as we wrap up this deep dive into the MyCESMM2 standard. We talked earlier about how the coding system is brilliantly future-proofed, leaving the Digit 9 completely open for entirely new descriptive features and technologies that don't even exist yet.
The innovation slot.
Right. So knowing how aggressively construction technology is advancing right now, what futuristic civil engineering methods or materials do you think estimators will be assigned